Thank you very much. The Honorary Frank Maguire, Parliamentary Secretary for Medical Research, the Victorian Government, distinguished visitors, presidents of global nuclear medicine societies and associations, friends and colleagues. It's my pleasure and privilege to welcome you to the opening plenary session of the 12th Congress of the World Federation of Nuclear Medicine and Biology. Now, since the first Congress of the World Federation in 1974, we've seen many changes in our specialty, which have changed our clinical practice and have led to improved diagnostic and therapeutic procedures for patients. And while there have been periods of rapid upward momentum in recent years, particularly the technology advances that we've seen with PET-CT and SPECT-CT, we're now seeing an acceleration in novel imaging radiopharmaceuticals being approved, despite the challenges we face of higher hurdles for regulatory approvals and reimbursement. But I am convinced that we are on the threshold of a new golden age for nuclear medicine, as we've seen remarkable progress in the last few years alone in therapeutic strategies such as with peptide receptor and radionuclide therapy, alpha emitters, locoregional therapies, and many more innovative approaches to molecular imaging for imaging biochemical, proteomic, metabolomic and genomic signatures in tissue. And in this regard, we have an unprecedented opportunity to exploit the power of the radiotracer principle to bring improved diagnostic and therapeutic options for our patients. The key to this success is by building teams, our chemists, our physicists and clinical professionals, together with scientists and clinicians from other disciplines. And we're seeing many examples of this successful approach. This also involves a multidisciplinary approach both to discovery and evidence-based prospective clinical trials that require new networks of engaged clinicians and scientists across specialties working together. I hope that you will find that this Congress provides an opportunity for you to ask yourself how to use these opportunities and more clearly understand how to approach the task ahead. And I encourage all of you, young and old, to be innovative, creative, and focus on how teams can bring greater results than individuals alone. Now, while the World Federation Congresses are held every 4 years and are equivalent to the Olympics of our profession and include the same intense bidding interest for hosting countries, I certainly found that to be the case for us. And when they are held, they bring a combination of pride, anticipation and intent to bring the highlights of the field to one unique event. And our journey to host this 12th Congress of the World Federation of Nuclear Medicine and Biology has taken 10 years. And our organising committee has worked diligently to create a program of world-class science and clinical talks, poster sessions and opportunities for engagement for attendees. And I'm very pleased to announce that we have now reached, as of this morning, 1,936 Congress attendees. So we do hope to reach that magical 2,000 barrier during this Congress. Interestingly, also representing 78 countries around the globe. So this clearly represents the largest conference of its type ever held in Australia, and I hope will be memorable for our Australian and international attendees. I would like to mention, however, that it is important to recognise that the World Federation is not just an organisation that runs a congress every 4 years, but it is the peak body for nuclear medicine globally. It aims to progress and promote nuclear medicine and the translation of molecular medicine throughout the regions of the world. And its principal goals are to promote advocacy, access, teaching and training, technical standards and therapy, particularly in developing countries. So in this context, our interaction with the major global nuclear medicine societies and associations and WHO and the International Atomic Energy Agency are critical in ensuring these aspirational programs are successfully achieved. And we're totally committed to working with our member countries to enhance communication, promote collaboration, and facilitate programs to enhance nuclear medicine practice. So in bringing this Congress to the start of the scientific program, I'm also very grateful for the continued support of a number of professional and government organisations in the creation of this Congress event. These include the Melbourne Convention Bureau and the Victorian Government, our diamond sponsor Chartwell Medical, our major sponsors ANSTO, GE, Philips and Siemens, our supporting partners Telix Pharmaceuticals, Theranostics Australia, Cyclomedica and IBA, and other key sponsors including SI, Emaxion and Ipsen, and of course all of our supporting associations. On behalf of the organising committee, thank you for all your support, and I'm confident that you will find this 12th Congress of the World Federation of Nuclear Medicine Biology rewarding, stimulating and enjoyable. Thank you very much. So I'd now like to welcome Professor Dale Bailey, President of the Australian-New Zealand Society of Nuclear Medicine, to say a few words.
Thank you, Andrew. Hosting this World Congress is the culmination of a decade of work from our local organising committee. We are delighted to see you here. We have put together, I think, a very packed program, high on scientific content and challenge for all of you. We are an Australian and New Zealand Society of Nuclear Medicine, and so from our New Zealand components, I'd say kia ora to all of you, and from Australia, g'day. Have a good Congress.
Thank you, Dale. We now have a message of greeting from the Director General of the International Atomic Energy Agency, Yukio Amano, that will now be presenting.
Ladies and gentlemen, I am very pleased to have an opportunity to say a few words to participants in the 2018 Congress of the World Federation of Nuclear Medicine and Biology. A key role of the International Atomic Energy Agency is to help developing countries to use nuclear science and technology in health, energy, food and agriculture, and many other areas. Improving access to radiotherapy and nuclear medicine is a priority for our 169 member states, especially for developing countries. The problems faced by developing countries in offering nuclear medicine are enormous. They include a shortage of qualified staff, lack of availability of radioisotopes and kits, erratic power supply, aged equipment, and a lack of local services facilities for equipment. Since 1958, the IAEA has been working to help countries deal with challenges such as these. We offer support in areas including cancer, neurological disorders such as Alzheimer's disease, and cardiovascular conditions. Ladies and gentlemen, in the last 40 years, the IAEA has implemented over 750 nuclear medicine projects in 138 countries. We arrange education and training for nuclear medicine physicians and radiopharmacists in more developed countries. We train medical physicists at our own nuclear applications laboratories near Vienna. In 2016, we presented the IAEA curricula for nuclear medicine professionals in order to provide a structured and continuous professional training program for specialists in the field. Our Human Health Campus website is a unique educational resource for professionals in medical physics, nuclear medicine, radiology, and related fields, providing insights into clinical practice. We assist countries in procuring equipment as well as with clinical research and dosimetry. At the policy level, we help governments to put national plans in place to offer comprehensive cancer care to their people. IAEA expert missions assess the level of nuclear medicine and radiotherapy services in a country and offer recommendations on improvements. We work closely with our member states on nuclear safety, helping to ensure that both patients and staff are protected from harmful exposure to radiation. Our dosimetry laboratory provides dosimetry auditing services for radiotherapy centers throughout the world, free of charge. The IAEA also supports important research projects. We have worked with more than 1,300 leading research institutions throughout the world on projects covering the 4 major pillars of nuclear medicine: cardiology, oncology, neurology, and infectious diseases. In short, the IAEA provides an extensive and comprehensive package of services which cover everything that a country needs in order to make optimal use of nuclear technology in healthcare. Ladies and gentlemen, I have seen some improvement in the availability of nuclear medicine and radiotherapy facilities in developing countries in the past 8 years, but the needs remain huge. My message to nuclear medicine professionals in more developed countries is, please share your considerable expertise with your colleagues in developing countries. Invite doctors, technologists, radiopharmacists, and medical physicists as IAEA fellows to your country or your institution for training. Offer your services as a teacher or lecturer on IAEA training programs. Take part in IAEA expert missions. All of these activities have real impact in saving lives in developing countries. Ladies and gentlemen, in the coming years, I will continue to do everything I can to help ensure that all countries will be able to make full use of the great benefit of nuclear medicine. I invite all of you to join us in that noble enterprise. Thank you.
And we thank Director General Amano for his kind words. I'd now like to introduce Frank Maguire, the Parliamentary Secretary for Medical Research from the Victorian Government, to say a few words.
Welcome to the world's most livable city. Congratulations on being here. I'm delighted to be opening the Olympic Games in the category of Best and Brightest. And the competition is for collaboration to help and to save lives. So I'd like to, in that way, acknowledge all the distinguished guests that are here. And if you've made it from around the world to be part of this delegation, you are by definition a distinguished guest. So what about a round of applause for everybody who's here and the collaborations to be made today. In the spirit of reconciliation, I'd like to acknowledge the original custodians of the land and the elders past, present and emerging from the world's longest continuous culture. And I do want to also single out our Nobel laureates. And we've got Professor Brian Schmidt, the Vice-Chancellor and President of the Australian University, here with us today, and Peter Doherty from the University of Melbourne also. And Peter, of course, has a medical research institution named after him right here in the heart of Melbourne. And it goes to acknowledge and underscore the commitment that we have to medical research, to science, and it comes, remember, at an important time because we've all prospered from enlightenment, and we're now at a time where facts are no longer seen as being stubborn but can be alternate. where the search for the obtainable truth was always a noble proposition, but now it can be disputed. So I want to encourage and give you the best support from the Victorian Government, Premier Daniel Andrews, Health Minister Jill Hennessy and myself, to see what you can do on collaboration, because now is the time when we need science to shine. And to give you an idea about our emphasis on collaboration, I saw President Barack Obama's final State of the Union address, and if you remember that, this is when he made his call for a new quest, and he challenged America to a new moonshot, the quest to try to cure cancer. And I remember he put Vice President Joe Biden in charge of what he called mission control. So immediately I put up the proposition that Australia should offer to partner, because the simple idea behind it was the more people, the more of the best and brightest that we have engaged in this, the faster that we will be able to make breakthroughs and discoveries. And it harked back to that time when American exceptionalism put Neil Armstrong on the moon in 1969, but Australian ingenuity brought those iconic photographs and that vision around the world. And that was through science. And it was through the satellite dish at Honeysuckle Creek outside Canberra. And it went to that whole proposition that here was a relationship not forged in war, but in the sea of tranquility. And that the measure of any country's enlightenment in a globalized 21st century will be its partnerships to save lives. So fundamentally, I've looked through your agenda and the depth of the science, the innovation that you're looking to create, and the breakthroughs that we're hoping that you will achieve, and just say that you've come to the right place. I make only one request. When you've made those elegant discoveries, ring me first, okay, if I can just say that. But we do look to collaborate with you, and I do want to underscore the importance of what you're doing, the respect and regard that we have for you, and while you are here, do make the most of the world's most livable city. All the best.
Thank you very much for those wonderful greetings and remarks. So it's my pleasure now to introduce the first of our main speakers in this opening plenary session. Particularly delighted that it's a very good friend to the global nuclear medicine community, Dr. Diana Paez, the head of the nuclear medicine section of the International Atomic Energy Agency. We very much look forward to her presentation. Diana.
So I will say thank you to the most livable city, Melbourne, for hosting us. And I hope you're ready to receive the 1,900 calls that you will receive from 78 member states. This is great. It is, for me, a privilege and an honor to be with you today at the opening session of the 12th Congress of the World Federation of Nuclear Medicine and Biology. I thank Professor Andrew Scott, Professor Setin Lee, Professor Dave Bailey, and the organizing committee for allowing me to address you today. During the conference, you will hear outstanding speakers presenting the latest scientific developments in the various fields of nuclear medicine. Nonetheless, my presentation will be slightly different. During the next 15 to 20 minutes, I will give you a global perspective of the nuclear medicine, just to set the scene. Let's start by analyzing the nuclear medicine imaging growing. We know that nuclear medicine is considered a growing segment of the healthcare landscape. The global market size of nuclear medicine was estimated in over $6 billion American dollars in 2016. And it is estimated to have a compound annual growth rate of over 10% from 2017 to 2023. Let's put this data in context. Let's compare this data with the global market of medical imaging. In total, medical imaging that comprise X-ray, ultrasound, CT, MR, and nuclear medicine, both SPECT and PET, had a value of over 33, almost 34 billion American dollars in 2014. The expected growth rate, annual growth rate, is 5.7 globally from 2018 to 2025. But what about other imaging modalities like the CT, the very popular CT? The global market of the CT in 2015 was almost $5 billion, and the expected growth is only 5% from 2016 to 2022. It is expected that the cities with the highest number of slides will be the ones that will drive the growth in the CT arena. And what about the MR, which is the other imaging modality? The global market size of the MR was estimated in close to $6 billion in 2015. The estimated annual growth for the MR from 2016 to 2021 is close to 6%. It is clear that the X-ray is the one that dominates the imaging market. And why is that? It's because the wider spectrum of applications, because the easy setting, and because the lower cost. But from these numbers, it is also clear that nuclear medicine is the one that perhaps will drive the market of medical imaging. And it is expected that Asia Pacific and Latin America will be the largest drivers of this growth. Good. Growing segment of the healthcare, but in any case, it remains the smallest sector in medical imaging when we see the number of installations worldwide. It will be the fastest growing because of the prevalence of non-communicable diseases. We know that the non-communicable diseases are on the rise. The incidence of cancer, cardiovascular diseases, neurological conditions is increasing. And nuclear medicine has an important role in the evaluation of this patient. It is estimated that approximately 52% of the premature deaths, considered people less than 70 years, are associated to non-communicable diseases, being cardiovascular diseases the number one killer, followed by cancer, and very closely by the neurological conditions. In addition, there is a continuous need for early and accurate diagnosis. That is why nuclear medicine also plays a very important role, and we expect it to drive the growth of medical imaging. What about the technological developments? We have unprecedented developments in both hardware and software that actually have changed the practice of nuclear medicine. Developing new tracers. Our best friends are the radiopharmacies that are helping us to develop tracers for research. And definitely the acceptance in the emerging markets are the drivers of the growth of the nuclear medicine. Again, let's try to put this data in context. Let's analyze the case of Latin America and the Caribbean. In the last 2 decades, the region experienced an important growth. But like in many other latitudes, there is an heterogeneous distribution of the technology and the human resources, capable human resources. So according to the data collected by the International Atomic Energy Agency, in the region, Latin America and the Caribbean, that has 33 countries, we have in 2015 approximately 1,200 cameras. 8% of this installed base are SPECT-CT or were SPECT-CT systems. But when you put this data like this, there are only 2.3 cameras per million inhabitants available in the 20 countries that have nuclear medicine in the region. When you compare this with data from developed country like Belgium, you can see the difference. In Belgium, there are 26 cameras per million inhabitants. It's not really fair to compare only with Belgium because Belgium has almost double the number of cameras than other countries in the regions. There are some countries that have between 10 to 20 cameras, Austria, Cyprus, Denmark, and Hungary. Majority of the countries have between 5 to 10 cameras, and there are some countries that have less than 5 cameras per million inhabitants. If you see the countries, majority of them are developing economies. Okay, what about the growth of the SPECT segment of the nuclear medicine diagnostic component in Europe from 2010 to 2015? There were a growth in mainly 2 countries, Croatia and France, but look what happened. Many countries actually, the number of cameras decreased. In the majority though, no changes were evident during this time period. Why do you think is that? Why is decreasing the SPECT market? Perhaps one reason is the shift from SPECT to SPECT-CT that was mentioned by Andrew. The clinical applications of SPECT-CT are better, more precise, so that is why there is a shift. According to the industry, the major vendors, the install base, remember that I mentioned that in Latin America was 8%, so now accounts for approximately 25% of the cameras installed. And the new sales, almost 50%, correspond to SPECT-CT systems. So it's definitely a change. And what about the per marker? Let's again take the example of Latin America and data collected by the IAEA from 2005 to 2015. In 2005 in Latin America, we have 22 PET-CT scanners in only 6 out of the 33 countries. What happened in 2015? 144 scanners in 12 countries. This represents an annual growth of 22%, which is higher than the expected 10% that we mentioned at the beginning of the talk. But again, when we put the data like this, we see that there are only 0.3 scanners per million inhabitants available in the region, which is far below the recommended 2 to 2.5 scanners, PET scanners in well-developed settings. It's important to mention that between 2015 to 2018, the growth actually continued at the same pace, 22%. And it was led by countries like Brazil, that went from 60 scanners to 110 scanners, Mexico, that went from 19 to 35, or Colombia, that went from 9 to 13. 2 additional countries acquired PET scanners or installed PET scanners in this time, Costa Rica and the Dominican Republic. Let's compare this data with Europe. Again, PET scanners in Europe in 2015. The countries with the largest number of scanners were Italy, France, and Germany. But the highest growth was in France. It went from 2000 to 2015 from 9 PET scanners to 130 PET scanners, representing a compound annual growth rate of 90%. But the majority of the countries did not have major changes in the number of cameras available per million inhabitants. The 2 countries with the highest number of cameras, PET scanners from million inhabitants, are Denmark and Malta, but the majority of the countries have 3 scanners, which is a little bit above the recommendation, 2 to 2.5 scanners in well-developed contexts. We are living in a world of unprecedented technological and scientific developments. So we have an increased demand for personalized medicine approach. But what is personalized medicine approach? Personalized medicine approach is no other than the development of better strategies for detecting and treating diseases based on the individual's unique profile. The growth of personalized medicine is propelled by various factors, like, for instance, it was mentioned by Andrew also, the advances in molecular biology, genetics, and proteomics, the better understanding of the normal and the pathological processes, the greater knowledge of the mechanisms of individual diseases, the superior identification of disease subtypes, and the better prediction of individual patient response to treatment. And when we talk about personalized medicine, we have to talk about the potential that nuclear medicine techniques has to contribute to that. So nuclear medicine has the potential to deliver improved healthcare, has the potential to reduce, this is extremely important, reduce the health expenditures, accelerate, simplify, and reduce the cost of research, and of course, facilitate the implementation of personalized medicine. What about the second component of the nuclear medicine? We already talked about the diagnostic component, SPECT, PET, and now let's see what's going on with the therapies. Yeah, the diagnostic component was the one that has the largest market share in 2016, but the therapies are growing, and it is expected that the therapies will drive the growth of nuclear medicine in the coming years. The radioisotopes, you in here will see that I put the alpha emitters, the beta emitters, and I put something different, brachytherapy. Why is that? Because the nuclear medicine therapies are performed by colleagues, radiation oncologists in some latitudes, radiation therapies in some latitudes. So that is why when they are evaluating the market, they include brachytherapy as part of the nuclear medicine therapy. The beta emitters dominated or have been dominating the market for the last years, but the alpha emitters are growing. However, we have some difficulties. We are in the phase of collecting data, but the regulatory issues, they really possess a hurdle on the growing of these radionuclide therapies. It is clear to us that nuclear medicine can contribute to screening in some specific cases, to early diagnosis, to the disease location and spread, and to the evaluation of prognosis. So we can say that we are going in nuclear medicine from beyond the visible to something else. We are helping in the selection of the appropriate therapies. We are allowing our referring physicians to evaluate the therapy response and perform the follow-up of the patients. And we are leading the path to personalized medicine. So we can say that in nuclear medicine, we are going from beyond the visible to beyond the target. So now, with all this, we have come to a fork in the road in the nuclear medicine. And the choices are two. The first one is, do we really want to continue being perceived as a specialty that does only lesion detection? And it is competing against the ever-growing spatial resolution of the anatomic modalities? Or we want to go to the road of the precision medicine, where the tumor biology and directing the treatment will be the path. When we talk a bit about this, we are talking about diagnostics. So we are going from beyond the visible to beyond the target to diagnostics. When we talk about diagnostics, we have to come to the motto of the Congress, the global translation molecular medicine. Definitely, we have seen that nuclear medicine has a great potential, but it is important to mention that there are also great challenges. The first one is the education and training of the nuclear medicine professionals. We have to train not only the newcomers, but the people that have been working in the field for years. Nuclear physicians, medical physicists, radiopharmacists, and the technologists. Extremely important. But do not forget the referring physicians, because at the end, they are the ones that are sending the patients to us. We have to work with our regulatory bodies in order to help them understand the need of having licenses for the new products, for the alpha therapies, for all the innovation. It is extremely important to include quality management as part of any nuclear medicine practice, small or large, private, university hospital-based. Extremely important also to work with the governments for the reimbursement of the nuclear medicine studies. And not only the reimbursement, we have to work with them in order to get the yearly increase that we should have. I heard the other day that in Australia you have been, the cost of the PET scanners are the same since 10 years or something like that. So we also have to work on that. And we have to be extremely aware of the trend of going from volume-based medicine to the value-based medicine. Value-based medicine defines value as the health outcomes achieved for patients relative to the cost of achieving them. So we have to really start learning a little bit about health economics. And I just want to conclude by mentioning that at the International Atomic Energy Agency, we are here to support you to develop and strengthen the practice of nuclear medicine in the diagnostic and therapeutic components. We can provide support in 4 equally important areas: education and training. It was mentioned by our Director General that we have a unique tool that is the IAEA Human Health Campus. The address is www.humanhealth.iaea.org. Quality, we can support you to implement quality management in your nuclear medicine practices. Research, also mentioned by the Director General, and services like dosimetry. With that, I conclude. I thank you very much for your attention, and I wish you all success in this conference. Thank you.
Thank you very much, Diana. We just have a small gift to thank you for this wonderful presentation during this Congress. Now, it gives me great pleasure to now introduce our other plenary speaker, Nobel laureate Professor Brian Schmidt, who is the Vice-Chancellor and President of the Australian National University. I'm sure he needs no further introduction, but we're very excited to have him here to give a presentation to us in this opening session. Brian.
Good morning, everyone, and it's great to be down in Melbourne from Canberra, and I welcome everyone who has arrived from around the world. So, as someone who studies, I would say, nuclear physics in the sky, there is a bit of a gap, a bit of a bridge between my knowledge and what you guys are discussing. And I've been asked to talk a little bit about the work I have done and try to relate it to the whole process of scientific discovery and inquiry in what is a very interesting time in the world. So before we start, I want to go back and think really big. And I want to think about humanity itself. And I'm going to start with where you are here in Melbourne. So you are here, as the minister told you, at a place that has been inhabited by more than 40,000 years by the Wurundjeri people of the Kulin Nation. And the minister, as we do here in Australia, has paid our respects to their elders, past, present, and as I always like to say, emerging. But I want you to think about what has been going on for this culture that has been here in Australia for more than 65,000 years, and how it relates to the culture that each and every one of us shares. And I'm going to do that with something of the stars. That is, when we look up in the sky, it turns out everyone here can see this constellation, which we call the Seven Sisters, or the Pleiades. These 7 stars, or actually it's many, many hundreds of stars, but you can only see 6, it turns out, with your eye, are visible everywhere on the planet. And there is a story here in Australia that goes across the whole land related to the 7 sisters, a story of how these stars, and one of them gets lost, relates to how they track and walk around landmarks across Australia. But the story should sound familiar, because if you're from Europe, of course, the whole story of the Pleiades is the 7 sisters story. And if you're from India, there is a similar story. From Thailand, a similar story. This is the same story, and it is a story that goes back to the beginnings of humanity, when we truly were all one people. And it's hard to imagine, because it seems unfathomable, but stories can persist. But the stories here in Melbourne involve the flooding of Port Phillip Bay when the last ice age ended, and that is in their stories as well. So every human has shared the stars, and they are a way to think about the plight we have, or the opportunities we have here on Earth. And just to show you how deep this is for your people from European backgrounds, this is in a cave in Europe, and you can see the bowl with the Pleiades there. Why is this significant? This is 17,300 years old. Well, what is the bull? The bull is Taurus, and the Pleiades is right on the shoulder of the bull, just like our constellations that we use today. That's 17,300 years old. This is all the same story. Most of you are probably in the Southern Hemisphere the first time, and I'm going to give you a little star tour, the real basics. If you look up, you will see the Southern Cross, pretty hard to miss, even in Melbourne. And if you look at the 2 bright stars that point to it, the brightest of those 2 stars is Alpha Centauri, the closest star to Earth, the closest stellar system to Earth, a mere 4.3 light years in distance. So 4.3 light years, just to give you your sense, is 4.3 years times 186,000 miles per second, or 300,000 kilometers per second, times 31 million seconds per year. It's a lot of distance. But of course, that's the nearest space we have. And we live in a much bigger system, which we'll talk about in a second. We are also living in a time of disruption. The so-called Fourth Industrial Revolution, you can call it whatever you want, is a new platform that we are all using and being enveloped by, and we are being disrupted by it. The rapid change of how we do things is going to affect each and every one of us in ways that are not yet apparent. And as though we are part of disruption, and what we're going to be talking about are new ways of using nuclear medicine, hopefully to advance humanity, we also have to realize that we are being disrupted. And the techniques that we have had in this field as the basis of what you do are likely to be replaced by completely different things that have nothing to do with you. But you will be producing, in turn, new things that have nothing to do with what you've done before. And you have to be prepared to move and actively manage that change, because the pace of change is unlike anything that most of us have dealt with in our lives. And it's very easy to get caught flat-footed. And in the end, things are changing now, And when things are changing, in the short term, things change less than you think, but 15, 20, 25 years, things change a lot more than you expect. And so it is very easy to just get left behind. Back to the stars. We live in a galaxy, shown here. This is an actual real picture looking out in the sky. A galaxy of 100 billion suns. And if you're very careful and you get out of Melbourne, you can actually see two satellite galaxies, the Large and Small Magellanic Clouds, that have about 1 billion and 10 billion stars each. And that galaxy is about 100,000 light years across. So we really are a drop in the ocean. Especially when you look much further afield and you zoom into a tiny piece of sky, for example, this piece of sky, which is about 1/13 of the entire sky, and you see it has roughly 20,000 galaxies, each of the same scale of our own Milky Way. The universe is very big, but that does not mean the Earth is unimportant. How remarkable it is that we can understand as much as we do about our universe from our tiny little planet in an insignificant galaxy in a sea of galaxies that is larger than you can imagine. You can look back even further. You can look back to the time of the Big Bang, 13.8 billion years ago, when the universe was hot and glowed like the sun. It is remarkable what we have learned to understand. And we have done that over the last 100 years, starting with our first cosmologist, observational cosmologist, Hubble. Hubble went out and was able to make measurements of the sky by measuring distances, by how bright things appeared, and then by measuring how fast they're moving by the Doppler shift. He was able to find a very funny thing. A funny thing that the further an object is away, the fainter its stars are. And the fainter an object's stars are would indicate, all other things being equal, the more distant the object is. And so this is the diagram that made Hubble extremely famous. And what he plotted in 1929 here is how bright stars were in a galaxy versus how much the light had been stretched by what he thought was the Doppler shift, which indicated the rate of recession towards, or as it turned out, everything was moving away. And what he found is that the further away you were, that is, the fainter your stars were, the faster motion away. And from that, he announced that meant that the universe was expanding. Why did he say that? Well, an easy cartoon. I have the universe, which I'm going to expand, and when I've expanded it, you can overlay before and after, and you can see in an expanding universe that the closer you are, the slower you're moving away as I've expanded the universe, the further away, the greater the expansion rate is. And so just like this cartoon, when I expand the universe, Hubble saw the closer, the slower, the further, the faster. Now, as in most areas of science, you need to tie together an observation with an underlying theory. And that underlying theory, as I'll show you, is general relativity. But before we do that, let's just think of what this means. If the universe is expanding, and I run it in reverse, you end up to a time when everything in the universe is on top of everything else. The time of the Big Bang is almost inevitable in an expanding universe. That is, it's a natural occurrence if the universe is getting bigger. So, why did it occur? We don't know. But the fact that it did is something that makes sense based on what we see. So, the universe began in something called a Big Bang. That, as I said, actually, the Big Bang itself we don't understand at all. What we understand is what happened right after the Big Bang, which is the universe was hot and it was expanding and created this pattern in the sky we called the cosmic microwave background 380,000 years later. And what you see in this image taken by the Planck satellite are sound waves that rippled around the universe. And those sound waves were caused by essentially the splash mark of the Big Bang, what we believe to be quantum fluctuations. So essentially the manifestation of the Heisenberg uncertainty principle, where things come in and out of existence. And the universe right after the Big Bang was inflated to a huge size. Something the size of an atom became the size of everything we know today. And that took those little quantum fluctuations and magnified them by 10 to the 60. So 10 to the 60 is a very large number, even if you're dealing with atoms. It's a very large number. And so what you're seeing in those bumps and wiggles are actually the tiniest things you can imagine, magnified by 10 to the 60, and allowed to rattle around the universe for 380,000 years as sound waves. Sounds crazy, except for it predicts exactly what we see there. And that idea happened in 1980, and we measured it starting in 2000 and have measured it more and more accurately. And to this day, in 2018, the theory, which has its origins in an idea in 1980, is exactly, essentially exactly reproduced in the observations of the day. Science doesn't always fit our intuition. When I was in graduate school, and that story was told to me because it came at Alan Guth, I was at Harvard, he was just down the road, and I thought it was fanciful, crazy. Come on, show me the data. Well, we got the data, and Alan Guth was more or less correct. So it is worthwhile to realize that we actually need to go measure things. And our gut feelings, no matter what we're doing, often correct, can be wrong. And we should continue to ensure, in an era where the people who, for example, most of you deal with in a legislative sense, very much tied to gut feelings. We know that can't be right. And you need to stick to evidence in everything you do. And this is a good story among many of where your gut feeling gets the wrong answer. So please stick to evidence in everything that we do, even if it's sometimes not the story you want to tell, because in the long term, it will give you the right story. All right, so I alluded earlier to Einstein's theory of gravity. We, to understand the universe, can't just take pretty pictures and then tell you a story. We have to have an underpinning understanding. And our theory comes from Einstein's thought in 1907, possibly when he saw a poor guy fall off a roof. And as the guy was falling to the ground, Einstein did not think, I need to get a doctor. Rather, I think that person doesn't feel any gravity. And I think that if anyone falls off a metaphorical roof anywhere in the universe, the acceleration will completely counteract the gravity, and they'll be indistinguishable. A tiny thought that took him 8 years to realize. So effectively, if you're in a box, you can't tell if you're in a rocket ship accelerating at 9.8 meters per second squared or on planet Earth being accelerated by 9.8 meters per second squared. The acceleration and the acceleration due to gravity are equivalent. So from that, he had to literally reinvent physics. And in 1915, after 8 hard years, he published his theory, which predicted the curvature of space, among other things. To this day, this theory, again, has managed to be tested dozens of times in a very substantive way and has never been shown to be wrong. It is completely, again, non-intuitive, but once again, seems to be the universe we live in. Now, let's think about what general relativity tells you. And you could use your intuition here. Imagine I have an expanding universe, and I want to look at the distance between 2 galaxies. Well, I can, of course, run the time backwards. And if I run the universe in reverse, I can take how fast the universe is expanding now, run it back, and I can see how old the universe is. This was a cool thing to do, and it's actually what I did for my PhD thesis, and measured that if you take the universe right now and you run it reverse, it takes about 14 billion years to go back in time. And so that number of 14 billion years is still, turns out I got the right answer in my thesis, but many, many people were working on it, so not my discovery, I'm afraid. The universe is about 14 billion years old. It turns out when we did that, we cheated a little bit because we ran the universe in reverse, assuming an assumption that that line was straight. But the universe is full of gravity, and that gravity should slow the universe down over time. And if the universe slows down over time, the universe would not be as old as we would otherwise think. So instead of 14 billion years old, it might have been 11. So when I moved to Australia, my pitch for my job moving to Australia was that I was going to measure how much the universe slowed down so we could get the age right. And there's profound consequences, because if you think of what happens in the future, if the universe isn't slowing down, it just gets bigger and bigger and bigger, goes on forever. If, on the other hand, the universe slows down a lot, then the universe will stop expanding sometime in the future, go in reverse, and will die in what I like to call the Gnab-Gib, or the Big Bang in reverse. So I always like to tell people, when you're working on something, make sure you can explain it to your grandparents. And I explained what I was doing to my grandparents, and they said, "Why are you doing this? Why do we care?" And I said, "Isn't this cool?" And they said, "Yeah, I guess. Why do we pay you to do this?" This sounds the same conversation I have with a minister. And I always say it's interesting, but in the end, it's useful. Because many of the people and techniques and stuff we're going to talk about how we solve this problem are translating in different and multitudes of ways across our lives. Not in a predictable way, unfortunately, but in ways nonetheless. All right, just to really bend your mind, in general relativity, I told you space is curved. So depending on how much stuff's in the universe, it turns out space has different curvature. And if the universe is heavy, it curves onto itself. If it's light, it curves away from itself. If it's just right, and it turns out Alan Guth predicted that the universe, by his theory, should be just right, then it actually behaves in a way that more or less makes sense to you. Triangles, for example, have 180 degrees interior angle sums. So all these things play together if you can figure out what the universe was doing over time. And so, as I said, that was my pitch when I moved to Australia in 1994, was to measure how fast the universe was expanding over time. And how would you do that? Well, the way you measure the expansion rate of the universe, and I did for my thesis, is I take a galaxy, I measure how far away it is, and I measure its redshift. And I divide the two, and that's the expansion rate right now. But imagine I look at a galaxy not nearby, but one that is billions of light years away. Then that light will have taken billions of years to reach us. I will therefore be not measuring the expansion rate now, but I will be measuring the expansion rate back in time. And so if you do that for many, many objects, you can imagine charting the course. Is the universe not changing its expansion rate in time? That means it's just going to go on forever. Or is it slowing down? And is it slowing down fast enough such that gravity wins or gravity loses, depending on what side of that trajectory the universe actually lies on? That was my big pitch for my job. Now, the tool I used, the biggest thermonuclear detonations in the universe, Type 1a supernovae. Type 1a supernovae occurs, we believe, when a dead remnant of a star, like our sun will be in 7 or 8 billion years, is in a relationship with another star. And at some point, that star will be donated material from its sibling and grow in mass. And Chandrasekhar showed in the late 1930s that if such a star, which it turns out to be made up of degenerate electrons, exceeds 1.383 times the mass of our sun, it will become unstable. And when it becomes unstable, it'll want to collapse. It will ignite the carbon and oxygen that this star is made in, and you'll get a thermonuclear runaway, which in a period of a few seconds creates 6/10 of a solar mass of radioactive isotopes, mainly nickel 56, which decays, which has a 6-day half-life. So 6/10 of a solar mass of radioactive isotopes is 200,000 Earths worth. They're big, and they're bright. They're 5 billion times brighter than our sun. They take about 20 days for the energy to leak out. They're so big and heavy that all the gamma rays and stuff get trapped and can't leak out. But over 20 days, they expand at 20% of the speed of light, give or take a bit, and then fade away into oblivion. But they create something that we can measure across the universe. We can measure the distances, it turns out, very accurately. Now, I was a normal kid. I grew up in Montana and Alaska in the United States. I had a scientist father, and I never thought I was going to be an astronomer, but I liked science. My father, as I said, was a biologist, and so I happened into astronomy, never thinking I would actually be an astronomer, but doing it because I didn't know what else to do with my life. Some of you may have found yourself in your current jobs in not a dissimilar place. Some of you will have always known what you want to do. But in 1994, I had just finished my PhD thesis, and I had been working with colleagues in Chile. My colleagues in Chile had figured out how to measure distances very accurately to these exploding stars. And as a 27-year-old, I convinced, with the help of Nick Sunsev here in Chile, now in Texas, a group of colleagues to go out and try to find these distant exploding stars and measure the past expansion history of the universe. This was a bold and audacious thing that a 27-year-old person thought of doing, not because I was brilliant, but because I was probably stupid and uninhibited by the whole daunting task of it all. But that's okay, and there's a lesson to be learned there. As I said, I was the second youngest person on this team. It was made up of my mentors. And our goal to measure the ultimate fate of the universe was big, but in the end, when you're trying to put together a team of the professors who have trained you, you have no authority. You have a great deal of enthusiasm and 100% of my time. And this turns out, having no authority has been great training for becoming the president of a university, because you have no authority as the president of a university either. You just have enthusiasm, and you try to get the great unwashed professoriate to march one way and hope the students don't riot in the other part of the university. But again, there's a lesson. How do we work successfully as teams? And this is going to be one of the things I want to talk about in the reigning time. Our challenges were actually very large. We were across 5 continents. We had personality conflicts amongst the people we were working with. We had no budget. I had $8,000. I spent $8,000 to win the Nobel Prize. So big science, this was big science, but it is not big budget. I had a problem personally in that I knew it was going to take 3.5 years to make the measurement, and I had a 3-year job. The good news is everyone was excited and there were no hangers-on. Everyone was in there trying to do this. And so with goodwill, I went and said, guess we'll just see what happens, and went on. And in the end, things turned out okay. But you need to have a rules-based order. And I'll give you an example. People need to have clarity when you're working in collaborations. What's the biggest issue in academia? Publication order, at least in astronomy. So we got everyone to agree in advance, and we did not deviate. I was the 18th author on our discovery. And I have to admit, in astronomy, 18th is not a good place to be, because there were 21 people on that paper, so you just got stuck at the end. But took a deep breath and said, everything will be okay, and everything was okay, but it required some faith. However, if we had not agreed, and I had tried when we suddenly made this big discovery to change the author order, the whole thing would have fallen over. So you have to believe in the systems that you have. And as you're collaborating and working, make sure you have clarity in what you're doing with your colleagues, or the system will not work. It was hard. This is an image of the sky taken back in the 1990s. And there's several thousand galaxies. That image has got 8 million pixels. 8 million pixels, you're like, oh yeah, my iPhone does that. Well, this is 1995, 1994. My iPhone is 10 times more powerful than the most powerful computer we had access to. It also has 35, or in my case, 128 times more memory than any computer we had. We were doing big data, so in those 3.5 years, we collected a terabyte of data. Now, a terabyte of data, again, but that was 1,000 disk drives, and I had no budget, okay? So we had to use techniques called artificial intelligence. Rings a bell. We had to use the techniques that we're developing out of computer science around big data. Now, those are things that you think of now, but this was 1995, and we did that because I had no budget. I had nothing I could do except for try to figure out ways to do this on the smell of an oily rag. And that made us quite innovative. And trying to go through and find the needle in the haystack, these supernovae, in those terabytes of data, there would have been roughly 25 supernovae. So in a given night, we would take 50 gigabytes of data, have to process it in a few hours, and find the needles in the haystack. And so the way we would do that was to look for the things that appeared. And my job, as the foolish young postdoc who thought of this, was to write the software that did this. Back before there were any libraries, and you had to do most of it from scratch. And I can tell you it was not pretty. Nothing I'm proud of here except for the fact that it sort of worked. And I say sort of worked. So here you see nothing on the 4th of April. A star has appeared. That star, 5 billion light years in distance. That means the Earth's 4.545 billion years old. This is 500 million years before the Earth was formed. We can look back in time quite remarkably. See what the universe was doing all those years ago. So I'm going to take you to Chile in one of our observing runs where we happen to have a film camera along. And here in the beautiful Atacama Desert of northern Chile, with the Cerro 4-meter telescope that had this very large digital camera on it, a unique instrument in some of the clearest skies in the world, we took data, a much younger me, and as this data comes down, we're running this software, and that software has to go through and sift through the data, but it's not very good. So we literally have a sweatshop of graduate students and postdocs from all these groups around the world who converge in La Serena, Chile, and help my software out with the final bits and saying, yeah, that one's okay and that one's not. So long process. We have to take the data, decide what's right, and then send it, that data, to not from Chile, to Hawaii, to the largest telescopes in the world up on Mauna Kea, the Keck telescopes, where we can go through and take a spectrum and figure out the redshift, the two things that we need. So the data in Chile is going to give us the distance, the data here, and Adam Rees, who won the Nobel Prize, and Alex Filippenko there. So that process was intense, it was interesting, and it yielded a very big surprise in 1998, which is that we were expecting, of course, the universe to be slowing down a little bit or slowing down a lot, but it was doing neither. If you look at this diagram, each exploding star has an error bar and measures how fast the universe was expanding. Not a single object is down in the part of the diagram where the universe is slowing down enough to eventually stop and go in reverse. And only a few are consistent with the part of the boxes that that the universe is slowing down at all. The analysis is, with about 99.9% confidence, that the universe was speeding up, that in the past the universe was expanding slower and it sped up. And that was a huge surprise. And of course, in 1997 and 8, when we were realizing this, my first thought was not that I had made a profound discovery, but that I had wasted 3.5 years of my life to get an answer that made no sense. But you go, you check your work. That was an interesting process as well, trying to get the entire team to go through and sign on to what was a crazy result. But it ended up with a paper, and I should say 2 papers, because we were in a tense competition with a group out of Berkeley, and we both got essentially the same answer at the same time. The story of this is actually almost like a fairy tale of science. I don't think it normally happens this way, but it was something that I was part of. And so in 2011, we were awarded the Nobel Prize. Here's the team from those 5 continents around the world. But the one thing, looking back in time, that I noticed when I saw this picture is there's not a single woman in that group. And that is something that reflected astronomy in 1995, but not something I'm proud of. We could have and should have done better. And my advice is to learn from our mistakes. You need many ways of thinking to solve problems. And you need to hire and work with people who are not the same as you, but people who are complementary to you. You need different expertise, different personalities, different cultures, genders, backgrounds, and ideologies to solve the complex problems we all work on. And so I encourage you to think very hard about how you create your teams and not make the mistake we did. Back in 1994, when I set up that team, I was very enthusiastic, and I didn't even think about that. And that is the thing that I regret most. But we do, from that result, have a crazy answer. An answer that says 70% of the universe is stuff that's pushing us away, pushing everything away. We call that dark energy. And it is something that every experiment since 1998 has shown that something like dark energy must be there. It must be roughly 70% of our universe. The other 30% of the universe that has gravity like we would normally expect, most of that is stuff, again, that's invisible. We call dark matter, and that's another talk to have. Only 5% of the universe we're embedded in are the atoms that we all study. And so that means we have a universe that you might think makes no sense. And it really doesn't. But it predicts everything, every measurement we can, and it has been able to do so more or less in advance since 1998. So as we go through and we look at what each of us is doing, the future of work, as I've discussed, is going to change. Here in Australia, we have 65,000 PhD students on our books, and they're with 58,000 academic staff. The average time to finish a PhD is 5 years. So that means we have a thermonuclear runaway of graduate students with a doubling time of 5 years. We need to realize that that is not a stable situation, and that the whole way that academia, research, PhDs is evolving has to change. There can be no other way, because I should also say the number of academic staff in Australia is growing by about 1% per year. So it's going very slowly. So our PhDs programs are still largely geared at creating future academics, where 90% plus are going to do something else. And I encourage each and every one of you, when you're working with researchers, whether they be students or postdocs or early career researchers, to make sure you think that you don't impose what your career was like 25 years ago on the current generation, because that is not fair. It is a different world. But we have amazing new platforms for doing complex tasks, and that's one of the other things. Again, we like to impose how we used to do things on our current generation. We spend time doing things the old way. So I show here on the one side Wolfram Alpha doing a very nice calculation symbolically of a differential equation. Now, I spent an entire semester of my life doing differential equations and learning how to do them and memorizing and doing again and again and again so I could do it. And at almost every university in the world, we continue to make students spend months doing things again and again and again. Now, I'm not saying that we should have all mathematics or related things be a black box. But if we want our students to get into the latest technology without being 50 before they're there, we're going to have to think about how we teach things. And mathematics, we need to go through and use these new techniques to accelerate what they're able to learn and have them learn the techniques and understand them. But then the rote part, I'm sorry, Wolfram Alpha and equivalent things can do it for you. You will never ever solve a second-order differential equation by hand again. Or if you do, you obviously enjoy it as a pastime, like a Sudoku puzzle. In your area, medical research, we often have students and staff spend endless hours doing repetitive tasks of sample preparation and moving it through. There are robots that do that now. And we have to just get in and invest rather than call a PhD someone doing a series of endless tasks, spending 5% on the analysis at the end. We have to adjust to this new world. And we have to realize the culture is changing. This is a cumulative fraction of number of papers with a number of authors of the most cited papers, 1985, 2000, and 2015. We are working in bigger and bigger teams, yet the structures of how we give each other accolades don't reflect those big teams very well. Again, we need a system that is developing. We need to be aware of it. So I'm on this paper where we had two neutron stars merge together and create the R process of all the heavy nucleids. This is a seminal discovery. It is a great piece. There's 3,700 authors on this paper. There are people like me who gathered a little bit of data, and there are 50 people whose theses are entirely this type of work. How do we go through and give credit where credit is due in these situations? I don't know, but we need to be aware of it as we do our research. These are things that are going to determine whether or not we have a vibrant research community or we have one which becomes increasingly less attractive. Already in physics, I find we are struggling to keep the best students. They are being sucked off by Google and Amazon. Occasionally bioinformatics, which I can live with. It is a world that is changing. So the times they are changing, and we do need to adapt. Agility is going to be the key, what we study, how we study it, how we remain relevant. But at the same time, I always like to remind people, be happy. Things are changing, but there's increased porosity between industry, universities, and research labs. And the broad range of emerging fields and industries are talent-starved, and the people doing this work are the people they need. The problem I have with the students and the staff is they want to do things the way it was 20 years ago, and they think somehow being involved in this new stuff isn't right. It's somehow less important. Now, this group is fairly applied, and that may not be an issue, but there will be people around you who think that way. If we allow that to occur, then we really are in trouble. All right, I'm going to finish on the future of the universe, just to make you feel really gloomy. Our universe is a battle right now of domination of dark energy, which is pushing, and dark matter, which is pulling. Dark energy, it turns out, has won the battle. It continues to push the universe apart. And the more space expands, dark energy, which is part of space itself becomes more and more dominant over time. So it can push harder and harder, and you end up with an exponential runaway such that even light from galaxies we see today in the future will be stretched and will not be able to go across the universe to reach us. So in the future, we're going to look out to a universe which has literally expanded away from us, fading into oblivion. So unless dark energy suddenly disappears, the universe will, at an ever-increasing rate, expand, fade away into oblivion, leaving us here on Earth as an astronomer without a job and nothing to see. Thank you very much.
So thank you very much, Brian, for an inspiring talk and really goes to the heart of what this conference is all about. Collaboration, working together, and hopefully we can achieve an upward trajectory reaching to the stars as well. So thank you, Brian. We have a small gift to thank you for this wonderful talk.
Thank you. Beautiful. Thank you.
So that concludes this opening plenary session. Thank you very much, and I hope you enjoy the rest of the day.